Okay, so in this one, and in the next set of videos, we want to talk about free damped harmonic oscillators. So this is different from what we were talking about before, because before we were talking about the undamped case. Um, and in the undamped case, something unrealistic emerged as sort of the description of the motion of this mass on the end of the spring. We got what's called simple harmonic motion, where we have a sinusoid which just went up and down forever and ever and ever. And what we should understand is that's not a realistic description of what happens in the universe that we live in. Because in the universe that we live in, there's always going to be some friction, some energy which is lost due to, you know, the ever increasing entropy of our universe. But anyway, hopefully when we install a non-zero damping term into our harmonic oscillator, we will end up seeing more realistic behaviors out of our harmonic oscillators. Not unlike what happened, for example, when we studied free fall. When we study free fall just under the influence of gravity and no other forces, we got something very unrealistic. We had a object which would fall and keep accelerating forever and ever and ever and ever. But this is not what we observe. It's the reason why skydivers, when they jump out of planes, don't end up in splats on the ground. It's because there's a force of air resistance which opposes the direction of motion. And once we took that into account, we were able to see the phenomenon of terminal velocity coming out in our model. Okay, so what are we going to see coming out when we install damping into our harmonic oscillators? That's the question. Okay, so we want to talk about free damped harmonic oscillators now. Oscillators. Okay, so the equation is the same. It's going to be mx double prime plus cx prime plus kx equals 0. This follows from Newton's second law, considering the two forces acting on the object as being Hooke's law, or the spring force, and the friction force. Right, good. We are going to do the following move, which is not unlike what we did last time. We're going to divide through by m. And it's going to look funny because the way I'm going to write the middle coefficient is 2p x prime. And I'll define what p is in just a moment. And don't forget the k over m is omega naught squared. I'll define that just as a reminder. So this is what our new equation is going to look like, where p is going to be c over 2m. And you might be asking yourself, why in the world do we have that 2 there? It's gonna make our calculations later cleaner, okay? And you're gonna see that in just a second. And omega naught is the same as it was last time. It's k over m, square root of k over m. Yeah? Okay, yes, hopefully this is clear and makes sense. Now we can write down the characteristic polynomial. And we get r squared plus 2pr plus omega naught squared is equal to 0. And remember that the nature of the solution to our differential equation, and hence to our harmonic oscillator, depends on the nature of the roots of this characteristic polynomial. And what determines the nature of the roots of this characteristic polynomial is, of course, the discriminant. We'll get to all of this. But yeah, let's go ahead and use the quadratic formula now to write down an expression for the roots of this characteristic polynomial. We're going to have r equals negative 2p plus or minus the square root of 2p squared, whole thing squared, so it's 4p squared, minus 4 times 1 times omega naught squared. So that's 4 omega naught squared. And this whole thing gets divided by 2. And now you see maybe the reason why we put in this 2 here and here. It's because we can factor out a 4 from this square root here, right? If we factor out that 4, since the square root of 4 is 2, there is a 2 here and a 2 there that we can factor out and have cancel with the 2 that's downstairs. So after simplification, the roots become negative p plus or minus the square root of p squared minus omega naught squared. The discriminant in this case is the thing underneath the square root. And that's going to discriminate between the different cases, the different types of solutions that we're going to see in our harmonic oscillator. So let's go through those different cases in turn. The first case is called overdamping. This is what it's called. An overdamped harmonic oscillator is one for which p squared minus omega naught squared is positive. Okay? Now, in this situation where p squared minus omega naught squared is some positive number, the square root of that positive number is some positive number, and we're going to have negative p plus or minus that number. In other words, we're going to get two distinct and real roots, negative p plus the square root of p squared minus omega naught squared, and negative p minus square root of p squared minus omega naught squared. Okay? So in other words, here we get two distinct real roots. All right. Neat. And let's think about these roots, okay? The first root, I'll call it R1, is going to be negative p plus the square root of p squared minus omega naught squared. And the second one I'll call R2. That'll be negative p minus the square root of p squared minus omega naught squared. Now, can we say anything about these roots? And yeah, I think we can. For example, look at R sub 2 first. I wish I wrote R sub 2 as R sub 1, but whatever. Look at R sub 2 first. Will you agree with me that this R sub 2 is negative? Why? Well, that's because negative p is negative. Remember, I should say, p here is clearly a positive constant. So negative p is negative. And we're taking this negative thing here and we're subtracting the square root of something. The square root of something real. So this is clearly going to be a negative number. A negative minus a negative is negative. Even more negative. Yeah? But what about R1? Can we say anything about the sign, S-I-G-N, of R sub 1? The answer is yes. Because look here. What can we say about the square root of p squared minus omega naught squared? Well, what we can say is that it's less than p, right? Because if omega naught squared were 0, which it's not, but if omega naught squared were 0, then we would be talking about the square root of p squared, which is p. You see what I'm saying? And then we would be taking negative p plus p. But now what we're doing here is we're taking a little bit away, something positive away from p squared with p squared minus omega naught squared. So the square root of that is going to be less than p. So in particular, when we take negative p and we add something which is a little bit less than p, not a little bit, with less than p, then what we know is that this is going to be negative. Also, both of these roots are negative. And why that's interesting is because in the overdamping case, what we get is the following. We can write down the solutions. I'm going to call them R1 and R2, but now the general solution in this case is x equals C1 times e to the R1t plus C2 times e to the R2t. And the point I want to make is that both this and that are decaying exponentials. They're decaying exponentials. So what we should expect is that as time goes forward in an overdamped harmonic oscillator, we're going to see the displacement of the object go to 0. let me show you what some graphs of some example curves of this kind of decaying phenomenon. And I'm going to just take this straight from the textbook here. Here is our textbook, and here is some pictures of overdamping. Let me just actually copy this image and move it over to our thing here, and I'll just plant it down. Allow paste, and there it is. How nice. Oh, this is a transparent image. Look at that. Okay, well, anyway. So here is an example of an overdamped harmonic oscillator. And hopefully what you see is that, even if you started out with some initial velocity, so it's going upwards and large, we're tracking x along this axis. We're tracking t along here, just to be clear. Okay, even if you give it some initial forward velocity, quickly it's going to come back and it's going to level out back to equilibrium position. Okay? This is very useful. This is saying that basically what overdamping is sort of saying is that the damping is so large that we can't even get oscillation going in our harmonic oscillator. Even though we don't see oscillation happening, we nonetheless call this a harmonic oscillator. It's just an overdamped one. Okay? Such oscillators are very useful. So, for example, have you ever experienced there are these things that are sometimes affixed to the top of doors. They're called dashpots. And their purpose is so that when you close a door, that the door doesn't slam into the door jamb, right? That it will slow down as the door closes and then sort of kind of more or less silently enter into the door jamb and close without causing too much of a ruckus or anything like that, right? You might want to you might think of that door jamb. It's like oftentimes a little device that you see at the top of the door that has a little hinge that closes the door. That's an example of an overdamped harmonic oscillator. Okay? And that's overdamping. Okay. The other thing that can happen is something called critical damping. So critical damping. Or critically damped harmonic oscillators. These are when p squared minus omega naught squared is exactly equal to 0. Now, in the real world, okay, it's going to be exceptionally rare that you see anything being exactly equal to 0. Okay, so you shouldn't think of critical damping as being all that physical, or rather all that relevant to the real world. But if you are curious about what happens in this situation, sure, we can talk about it, right? Because what we see here is that the roots of our characteristic polynomial, look here, if p squared minus omega naught squared is 0, then this whole term right here dies. And what we're left with is what's called a repeated root. Now we have the terminology. It's a root of multiplicity 2. And what is that root? It's negative p. Okay, so what we're going to see in this case, the general solution is going to be x equals c1 e to the negative p t plus c2 times t e to the negative pt. Remember, that's how we deal with a repeated root. Okay? And now we see that what's going on here is we again have a decaying exponential. Okay, it's going to have very similar effects. But again, critical damping is just not very realistic, right? It's just not all that realistic because it is exceptionally rare to see p squared minus omega naught squared being exactly equal to 0 on the nose. Okay? It's the next video where, and I'll stop here, but in the next video, I want to talk about the underdamped case, because that maybe is the most interesting. And we're going to, take a very close look there at the underdamped case. Okay, see you in the next one.